Welcome to the Water Resources Podcast. I'm your host, Bridget Scanlon, from the Bureau of Economic Geology at the University of Texas at Austin. This podcast is produced in partnership with the National Academy of Engineering. In this podcast, we discuss water challenges with leading experts.
We are pleased to have Dr. Charles Vorosmarty to talk with us today on the podcast. Charles is the founding director of the Environmental Sciences Initiative at the Advanced Science Research Center at City University of New York. And prior to that, he worked for a couple of decades at the University of New Hampshire. And he's been involved in many programs, both nationally and internationally, related to water. But one of the ones that I would just point out is his involvement in the global scale indicators of water stress and advising United Nations delegates who negotiated water-related sustainable development goals. So today, I hope we will initially talk about water conflicts and how the tools he uses to map those. And then precursor to that was his work on mapping human water security and biodiversity threats, and then quantifying those threats and evaluating the global variability. And then most important of all, a lot of Charlie's work emphasizes solutions to these water threats, and these include green and grey solutions. So thank you so much, Charlie, for joining me today, and I really appreciate your taking the time. So I guess first, maybe I would love to talk about, water conflict, which is a big issue today, as we see in Ukraine and Israel. But you had done some work on mapping water conflict in Hungary and water conflict index. And maybe you could describe that a little bit, Charlie, and what you put in, what the drivers of that were and how you mapped it.
Okay. Well, thank you very much for the opportunity to chat with you today, as we have many times before in the past. And I find that your questions are really aiming at the heart of the water security questions that many of us are studying now. So that's really great to be sharing my ideas along with the others you've interviewed so far. So in terms of conflict, I'd like to begin by simply summarizing the fact that in many domains, there is this misconception that water conflicts are brewing everywhere across the planet and ready to burst out into armed conflict. I would like to say that the literature on the subject shows that water is actually a source of collaboration and cooperation. And there are many more examples of different countries, and even within countries, different provinces and states, cooperating on issues of water rather than creating ultimately a source of conflict. So the real challenge we have in the future is to make sure that the notion of collaboration and cooperation around water and dialogue around water is managed successfully so that we can avoid the more disastrous effects of conflict as we see unfolding in many parts of the world already. So from that sort of a socio-political perspective, we began to map out some of the potential pinch points or limits to the capacity of different areas of the globe to handle their water conflict problems. And what we did is we first of all looked at the issue of climate variability. And as we all know, we are anticipating that the statistics of water availability that's embedded in the whole climate change question, that's all changing. We are no longer in a stationary world. The statistics are changing. The elements of the extremes are exchanging, both in terms of water scarcity or too much water, in terms of flooding. And this is going to put a signature, a geophysical signature, into how humans are going to be using and ultimately having to cooperate over the water resource. Now, one of the things that I like to point out in terms of the kind of mapping that one could do at this point, there's the peculiarity of humans living in watersheds, and that is that they have areas that are upstream, midstream, and downstream of each other. And this is what really does pose the issue with respect to conflict, because there are going to be areas of a large watershed that ultimately is the source area for water. And if it's not taken care of correctly, if it's not overused, and if it's polluted, etc., it's going to create a signal in the midsection and the downstream area of the watershed. And since people live throughout the watershed, you all of a sudden can begin to map out these contrasts of haves and have-nots. People who can control the water, for example, if there are lots of dams and reservoirs upstream, obviously that's going to create a problem for those who are depending on water, let's say for irrigation in a dry part of the world. And so one of the tacit assumptions that we put into our mapping was that you can actually geographically assign where there are people, where the water resources are coming from, how they're being used, how they're creating potential disparities in the resource at a drainage basin scale. And that's the fundamental thing that we're trying to map. Now, on top of the climate and the variability that I just spoke of, and then on top of the almost geomorphologic organization of these problems, on top of it, you have haves and have-nots with respect to technical capacity to manage their water appropriately. You have differences in how land cover and land use is managed in different parts of the world that create potentially disastrous signals emanating from the upstream to the downstream. For example, if there's major deforestation upstream, you're sure to be seeing lots of erosion coming down rivers. And if you have invested in reservoirs, those reservoirs lose their value because they silt up over the years. And in addition, you could follow these signals right down to the coastal zone, where the coastal zone is now today starved for much of the sediment that used to flow into the coastal zone from the continents because of these large reservoir systems that we've put in place. So when you integrate all of this information, you can begin to get patterns of this potential stress. Not to say that it's going to result in an armed conflict, but you could use it to navigate where you need to, for example, spearhead some diplomatic interventions before you get to a problem where there's going to be real fights about who's going to get the water, how you're going to handle it, and et cetera. And there's a whole body of literature that has documented how the many treaties built around water are really keeping the peace. And again, if we look to the future with a more variable climate, there are going to be haves and have-nots that are unanticipated right now. Having a tool to presage where that's all going to play itself out, I think is an important step forward.
Yeah, I mean, I think it's great to see this, so that at least we have data to look at and try to prepare for these things. And I'm impressed with how detailed you have built these mapping indices. I mean, you have up to 23 stressors under different categories, and a lot of them related to watershed disturbance, pollution, water use management, and then also biotic factors. And then you put that on top of your climate variability stress index, which is your droughts and floods and and that aspect. And then you also consider the human factors, which I guess is whether you're dealing with transboundary systems like rivers that cross different countries, like you mentioned, the Rhine or the Danube or other rivers. And then it seemed like you also use some data from the Funds for Peace program, which I think emphasizes what you're talking about. You can use these to develop treaties to avoid conflict. This is a lot of information, and I like, what you say about the rivers being a network, parlaying things from upstream to downstream, and oftentimes downstream is where much of the population resides, but they may be impacted by upstream conditions. So this is really impressive, and I think extremely valuable as we have more issues with climate extremes and water scarcity and contamination. I guess some, they may not be directly related to conflict, but some extreme droughts, like the Syrian droughts in the late 2000s, water issues contributed to the conflict there. And also the example of the Grand Ethiopian Reservoir dam, the GERD, and that impacts on Egypt and stuff. So I think we will be dealing with more of these issues as we go forward with population growth and more development.
Yeah, I think one of the trends that we continue to see, in particular across the developing world, the rapidly developing world, I should say, is just like we did in the global north. We have instituted all manner of water engineering to control the vagaries of nature, to flatten out the variability of hydrographs so that we can get sustained water supplies in place. And we've built an enormous amount of water storage globally, in particular starting in the global north. But we constantly have been attempting to upgrade those pieces of infrastructure. But in many parts of the world, the global south, they're installing brand new systems that are mimicking what we may have done in the global north, let's say 100 years ago or 150 years ago, where you can actually look at the westward expansion of the U.S., not only in terms of people and the economy going from east to west, but you could plot this up as you see dams and reservoirs following the people as they move across the nation, and they're simply trying to assure water security as they inhabit different parts of the frontier. And it's a really fascinating story that you could tell for the history of the United States and its water infrastructure. But you see the exact same thing happening in places like Brazil or happening in Southeast Asia or Africa. And you see that there's this almost a knee-jerk response to humans developing an area. And what they do is they build water infrastructure, often very expensive types of infrastructure. And our group has been trying to, with colleagues, trying to articulate the value not only of well-engineered traditional systems like dams and reservoirs and water treatment systems and sewage treatment plants, et cetera, to protect the environment, but using green infrastructure, using nature's ecosystem services that are actually, if you organize them into a water delivery system together with the traditional engineering, you get these very collaborative green-gray infrastructure systems working together. And they work together from not only the standpoint of just becoming more reliable, but they also are a very cost-effective means by which you can produce a sustainable water supply that's not in need of great remediation before you, for example, pump it into a city and have it encounter the end users. So we're talking about ecosystems that can modify pollution loads through the use of wetlands, engineered or otherwise. You're talking about intact watersheds that does not allow the incursion of humans and sources of pollution or sources of land use that include potentially grazing land or any agriculture, industrial agriculture, which is going to create agrochemical pollution. It's going to create erosion sources. It's going to create a problem when you try to then process that water from the green infrastructure. Even though it's damaged, you're going to rely on it to then supply, for example, an urban watershed like in New York City situation. And we do our best in New York to try to protect that watershed that feeds into the New York City water supply, because otherwise the problem's going to be that you're going to increase the cost of doing business for your water security because you're trying to remediate the problems that had arisen by poor environmental stewardship. So I think the notion here is you combine green and gray infrastructures in a way that preserves the functionality of both to an optimal level. And from several studies, we can see that that's a much more cost-effective way of delivering your water security services.
Right. And talking about water security services, I think your study in 2010 that was published in Nature in 2010 on global threats to human water security and river biodiversity was comprehensive and transformative in the way we looked at these issues, combining both water for humans and water for ecosystems. I think that was very valuable and at a global scale, and again harmonizing many different data sources such as catchment disturbance, pollution, water resource development, and various biotic factors. And the results of, and then you translated that, you routed those drivers downstream then to show the impacts of downstream populations. And the results of that analysis were pretty daunting. I mean, indicating that 80% of the global population were exposed to high levels of threat to water security, and maybe about 65% of the river discharge was threatened in terms of biodiversity. So maybe you could describe that study, which your water security study, the conflict study built on. I think this was foundational for some of that other work.
Yeah, so the study that you just mentioned was an attempt to try to take stock, basically a snapshot at around the turn of the century, circa 2000, where we identified through a series of expert consultations, we identified the major factors that we have learned over the years have affected watersheds and have affected water security. So as you mentioned, we're looking at land cover disturbances. We were looking at the types of water management that was or is instituted in different parts of the world. We looked at biotic sources of potential stress through introduced species, exotic species coming into ecosystems where they don't really belong. And pollution. And from, again, a variety of studies, very broad literature on these different factors, we were able to identify a set of 23 indicators of these different themes, these broad themes that were imminently mappable. And so what we did is we assembled these data sets, which I should incidentally say, we're not derived in all cases for this study, they were repurposed for our study because they were produced as a consequence of some other piece of research that a team was working on. For example, the land cover data sets might have been very easily finding their way into global carbon balance studies. But we took that information and we interpreted it from the standpoint of landscape and watershed stewardship from a water resources perspective. So we took these mappable entities and we put them together. And one of the things that we initially were quite surprised about was that when you accumulate these stressors, you can begin to colorize the maps, and the more conjoined stresses there are in a particular area, the deeper the color red. Red meant danger and threat to the water system. And what we were surprised about when we first put this whole thing together was that, well, first of all, China, a place like India, rapidly developing, lots of people, perhaps not much of a history of environmental stewardship up to that point. You would expect them to have deep red colors. In fact, you do see that on the maps that we make. But contrary to what we thought, you see in places like Europe and the United States that these threats have accumulated and they're showing up as global hotspots. They're red areas. And this really had us scratching our heads because we thought that in looking at a place like the United States or Europe, which they have highly educated populations relative to other parts of the world, high technical capacity to institute integrated water resource management, and in financially better situation to control these problems. What we find instead is that there is almost a embedded philosophy of impairing these systems in the background, allowing, in some sense, the water resource supply system to become polluted or overused or have different kinds of land cover, human-dominated land covers come into these systems and threaten them. And then what we do, though, is we allow this impairment to happen, but then we repair the damage. And we repair the damage and make the water usable for the end user, the human end users, be they people who irrigate their cropland, people who are drinking the water, people who are using it for industrial purposes, use of water for cooling, power stations, etc. This panoply of engineering can reverse all of that maladaptive, impaired water resource, but at a very, very, very high price. So that if you look at the positive impact of traditional engineering in Europe and in the United States, you see that it completely reverses the high levels of threat we mapped out in the ambient environment. And again, this doesn't make a lot of sense because you think that places in the United States, they have an environmental protection agency. In point of fact, that doesn't do such a great job of protecting the water resource systems writ large. And when you do map this out at the regional, continental, and global scale, you see these major patterns, and you see the impact of water engineering to improve water at the point of delivery, at the point of use, in these areas that are rich enough to afford it. But in the global south, where they're still struggling with just the basics of water security, they cannot reverse those trends. And in some sense, they're stranded in this, this arena of impaired waterways that they then have to struggle with to try to clean up and use, for example, for an urban water supply. And so we came up with this notion that there's an impairment and a repairing of the system, and that's the way the The system has evolved for literally centuries. I've worked with some historians who look back at this, and we find that time and time again, humans, when they begin to interact with their water systems, they impair the water systems. And then what do? They either find a new water supply or they have to repair the systems at great expense to try to make it usable for human society. Our argument from at least a economic standpoint is that this has incurred literally trillions of dollars of investment in remediation, where you could, for literally dimes on the dollar, through environmental protection, get the same benefit as you do by investing in very expensive remediation engineering technologies. And that's the global story that we can now, I think, fairly securely paint. I think that's the picture that we've come up with, and I think we can defend that at this point.
Yeah, I think that was a fascinating aspect of that study, that where you had high population density and a lot of development, you had this high water security threat. But then in the countries, the economically developed countries or the highly developed countries that had the economics to generate the traditional engineering infrastructure, they could reverse those threats. And you developed an index called investment benefits factor. And much of that was related to dams, building of dams, as you mentioned earlier, to regulate flows and ensure continuous supply. And then reduce water use to maybe more below a sustainable threshold, and access to clean drinking water, which was like treating the water at the point of use. Right. So you weren't maybe resolving the issue at the source, but you were treating the water where you were using it. So I think what I like about your work is that a lot of people talk about water scarcity and focus on water quantity, but you consider quantity and quality issues. And then you also bring in economics into it, which is a real challenge and very impressive. And so it seems like the paradigm then is impair and repair. But what you were saying earlier, it would be nice if you could retain the natural capital that countries have initially without destroying it, and then go towards a more hybrid green-gray solution to solving problems. And some countries are more set up for this, right? Like South America, or seems to have more natural capital than other countries. Maybe you can describe that a little bit, like the forested watersheds and the wetlands and things like that.
Okay. So what we're seeing on the horizon into the future, we've done some forecasts. So we've looked at where we were at the beginning of the century, and that kind of carries you into the present and then off into the future. And we've been making some estimates mid-century recently. And one of the things that we, first of all, have seen from the economic investment literature is that as a simple consequence of economic development, and among the Sustainable Development Goals, the alleviation of poverty in its harshest forms and the creation of economic well-being is a centerpiece of the Sustainable Development Goals. Now, from a water security standpoint, if we are anticipating human wealth and well-being to be improved in general over time, what that's going to mean if we don't do business a little bit differently is that with each unit of wealth that a nation can accumulate, we're going to expect a unit growth in engineered infrastructure for water security. That's kind of almost a development law, and I could show you some statistics that play out pretty well to show that happening. So our expectation is, just as it happened in the developed world, the developing world over the next several decades is going to greatly enlarge and rely upon water engineering for its basic water security. That's fully anticipated. Now, you can do that with the engineering, either by choice, if you have enough green infrastructure to rely upon, or if you don't have that green infrastructure because your environment is severely degraded generally, there's not enough green space to produce the clean water supplies, let's say for a city, you're going to be forced to invest solely or mainly in this engineered infrastructure, which is very, very costly relative to the ecosystem services that a well-managed watershed that feeds into a public water supply would benefit you with. Okay, so what we're seeing is that these costs are in the trillions of dollars, and by destroying nature, or at least not using nature appropriately in these water security schemes, you're losing literally by mid-century trillions of dollars of value in the ecosystem not performing, and you having to replace that function with rather expensive engineering. So there's this real shell game that's going to be going on over the next many decades, with some countries like India, for example, that has not got a lot of unused space, unused green space. Its water resource background systems are going to be impaired, and they're going to have to repair them with this very, very costly engineering. Places like Africa that are rapidly developing, or a place like southeastern Brazil, there's much more green infrastructure that's not been degraded that you can rely upon to enhance your water security with the engineering. So you can put these tandem systems, these blended gray-green systems together, or at least there's the opportunity to do so. The choice might be not to go in that direction, which we think would be a painful economic decision, because those ecosystem resources are sitting there with these free services that you can really get a running start on your water security if you also have environmental security in these watersheds that you're managing.
Right. And I mean, that's extremely interesting. And you mentioned in that report, a green-grey path to global water security and sustainable infrastructure, that the costs from traditional engineering approaches would be 3 times that if you had maintained the natural capital and the forested uplands and the wetlands and things like that. So it'd be like 0.7 trillion to 2.3 trillion by 2050. So that would be the difference. So huge estimated economic benefits to retain that natural capital, but it's already too late in some countries like India and Southeast Asia, but possibly much of Central Africa and parts of South America could optimize development to retain some of that natural capital and avoid some of those engineering costs. So this impair and repair paradigm, I mean, and then the impacts on the rivers. So I guess that also suggests that maybe you could rely on the existing or expand the protected areas, and what role protected areas have in water resources. I know you've done some analysis of that, Charlie. Maybe you can describe that a little bit.
Yeah, well, we were hoping that by bringing together these different data sets of potential impairment and threats of these different categories, bringing that together with human populations, bringing that together with the hydrology of the rivers and the climate systems and all, that we could begin to make some statements about the state of affairs with respect to the green and the gray infrastructure roles that we could have in terms of the sustainable development of water. Now, one of the things that we were hoping for is that there have been, at least on paper, and there's been the declaration of large tracts of land that have been put into protected areas. And a protected area, you would reckon, would have the least water-related threat. And since it's protected, you would be getting good, reliable, clean water resources from those landscapes. As it turns out, about 2/3 of the world's population lives downstream of protected areas, okay? But what we found is that despite the designation of an area being protected, about 80% of the people who are served by those protected areas are actually exposed to high levels of threat. And that has to do with the fact that the protection is incomplete. It's not full coverage. It has a bleed over effect, for example, from atmospheric pollution blowing to the different watersheds from the atmosphere. And you have all sorts of these other background level human activities that are threatening these very systems that you find are protected. And in fact, the great irony here is Rob McDonald, a colleague of ours, published a very, very interesting paper with looking at, I think it was over 300 cities, urban areas. And he looked at the urban watersheds, or the watersheds that were serving the urban water supply, fresh water supply. And what he found that was that over a century period, despite the fact that these should be protected areas, I mean, after all, they're serving millions of people, hopefully with clean and reliable water supplies. But what he found was that the majority of these systems showed human incursion in terms of people populating the watersheds, people creating cropland and fertilizing those systems, and creating erosion and creating nutrient problems for the runoff that comes off those landscapes. And these weren't really protected watersheds, even though they are protected. Now, as we said before, if you don't protect those watersheds, you don't use the green infrastructure correctly, and even if it's a protected area, you find that you've got to pay a higher price. And he also documented the fact that there was a substantial increase in the treatment costs for those urban water supply systems that were not being appropriately managed in terms of those upstream landscapes. So he looked at this as a much more detailed way. We're looking at it kind of as a global mapping exercise, but they're both studies and both messages are completely in harmony with each other. That if you do degrade your environment, at the end of that party, let's just say, you're going to get a pretty big bill that you have to pay.
Right. And I guess some examples of that, as you mentioned earlier, was New York City, you know, the upland forests there that provide clean water and reduce your water treatment costs then for water supplies for New York City. And also, I think Sao Paulo and some other basins, you know, if they maintain the forests in the upland areas, then they would reduce the sediment load and reduce the treatment costs for the urban settings. So that's a trade-off that needs to be considered. And I guess, you know, building on all of this then, Charlie, it seems like recently you have been expanding and looking at food and energy and water aspects with the analysis of the Northeast and the Midwest and the trade-offs there and what could be done to secure water supplies or to deal with, you know, droughts, floods, these sorts of things. Maybe you could briefly describe some of that work.
Sure. So, you know, one of the important developments in the water resource domain in terms of coalescing our thinking, it was this idea of food, energy, and water as a nexus. You can't really be talking about food security without having enough water, either through rain-fed agriculture, through irrigation. Your energy systems require enormous amounts of water to operate. For example, power stations that have once-through cooling require prodigious amounts of that cooling water. And you could imagine with climate changing and with seasonal shortages or abundances of water, you have very, very different capabilities for cooling those power stations. So there's a water limitation on the production of the energy. And depending on how you manage your water, you might also affect the amount of water left over, so to speak, for the irrigators. And so, and on top of that, you have industrial demands for water. You have municipal water supply requirements to sustain populations. So all of a sudden, this nexus of food, energy, and water also has humans embedded in the whole thing. And one of the things that we're trying to do right now in a study of the northeastern US and Midwestern US is to look once again at this engineered set of interventions to bring about your food, energy, water security versus the green infrastructure, the natural capital. So you have traditional infrastructure and green infrastructure, okay? And we've argued that if you make a significant enough attempt at accounting for these different infrastructures, you can actually view the green and the gray as levers that you could pull, management levers that you could pull at the fully regional scale to bring about your improvement in water systems. Now, one example is in the realm of water pollution. And what we can do now is we can map out with great spatial specificity, for example, where are the point source loadings into river systems from urban and suburban water supply, wastewater, okay? And we have thousands of these wastewater supply systems mapped out onto our river networks. And we could ask the question, how much work did that traditional engineering infrastructure do before that pollutant got into the water supply? How much did you clean up before it got into a river, which could be a water supply to someone downstream? And we can map this out, and we could ask the same question. Well, once the nutrients get into the water system, what's the role of natural self-processing by the ecosystems? The ecosystem service, self-purification by the aquatic ecosystem. How much of that is happening in the Northeast and the Midwest? And we find a couple of very interesting things. The answer depends on where you're loading the pollutant, where the people are, and what the geomorphology of the rivers are. So if you start loading sewage or residual untreated sewage, or what you couldn't quite take care of 100% from that wastewater treatment plant, and you put it into a receiving water, you find that in the Northeast, the rivers generally are shorter with their transit times to the coastal zone, so that the ecosystems in the aquatic environment can only do so much. They don't have much of an opportunity to continue to clean that water as it came out of the sewage treatment facilities, okay? Now, if you look in the Midwest, given the fact that it's got these major watersheds that feed into the Mississippi Basin at large, they have huge lengths of river that can be viewed as a treatment and a polishing step on any of the residual nitrogen or phosphorus that you put into the receiving waters. They have another shot at being cleansed because of the natural green infrastructure embodied in the aquatic ecosystems. And so you can see these patterns at the regional scale. And if you had decisions to make about whether if you had $1 billion to spend, would you spend that $1 billion on upgrading sewage treatment plants or protecting the waterways that give you these free ecosystem services? That's an interesting trade-off that we'd have to have a dialogue with policymakers and economists about. But I think what we're able to demonstrate is that at the fully regional scale, you've got these major management alternatives and dials to spin and levers to pull in different ways, and you can optimize. I'm sure that you could optimize those in terms of how you invest the dollars in the future.
Wow, that's incredible. And our traditional approach is just to put in some engineering structure. You know, we can see it, we know exactly what it's doing, but we are learning more and more about what the ecosystems can do, and then understanding the trade-offs. So thank you so much, Charlie. Our guest today is Charlie Vorosmarty, and he's at the Environmental Sciences Initiative at the Advanced Science Research Center at City University of New York. And we talked about today mostly about conflicts, conflict mapping, water conflicts, and then human water security and biodiversity threats, and quantifying them, and green and gray solutions. And I really appreciate your work, Charlie. You were a pioneer in global hydrology, and your work incorporated both quantity and quality issues, and also economics and human development. So really helped us to think more broadly about water security and other related aspects. So thank you for taking the time.
Thank you, and I'd like to thank you for that nice set of accolades. But I should mention that it was not just me. I work with teams of people, and I have to acknowledge, you know, the scores of people that I've worked with on these very issues. And when we publish the papers, these are team-based efforts, much larger than what any single person could do. So, thanks for acknowledging us. Great.
Okay. Take care.